Hello, welcome back. In the next lecture, we talk about how to solve this Hit equation using Junior. And in this lecture, we will try to solve this equation in ADCME. The difference is that when you solve this partial differential equation in Junior, you do not create a computational graph. And in ADCME, you will create a computational graph, which you will rely on to calculate the gradients automatically at a later time. And this is a very important difference. If you do not need to create a computational graph, such as in Junior, then the computation will become very efficient because you can just release the memory immediately after you use it. But when you create a computational graph, you have to store everything, such as the intermediate results. So at a later stage, you can calculate the gradients using the backpropagation. So let's see how we can code this discretization using ADCME. So this is the same code I just copied from the Hit equation we implemented in the last lecture. And yeah, everything is specified here. And the main concept for ADCME is to detect which variables are optimizable and which are not. For example, in the inverse modeling, we want to find A and B from our data. So we will specify A and B as variables. So this is somewhere we need to change from the original program. So we specify them as variable. Oh, and of course you need to use ADCME first. Okay, so when you specify A and B to be variables, everything that depends on A and B will also become a tensor instead of a numerical value. Yeah, let's execute it and see what it outputs. So you can see that A is a tensor now, and B is also a tensor. And you can see kappa depends on A and B. You do not need a dot here because everything is automatically interpreted as element-wise operation if they are tensors. So you will see that kappa is also a tensor, so it's not a value anymore. And lambda will also be a tensor, and f will, f does not depend on A and B, so it can still be it can also be a numerical value. But you can also convert it to a tensor by just adding a constant here. So maybe we just add a constant, so we can have access to the tensor operations, to all the tensor operations, all the functions on tensors. So the challenge here is how to create a sparse matrix A. To create a sparse matrix, there's a function called spdeg, and this function will help you create a sparse matrix using tensors, and you can still do automatic differentiation with respect to the entries in the sparse tensor. In the sparse, actually it's a sparse matrix. Okay, and actually the syntax is kind of different, but it's very similar to spdeg-m, and you need to put pairs here, and you also need integer to specify the size of this matrix. So what's the size of A? The size of A, let's just change it to sparse deg. The size of A should be n, because we have n variables. So for this negative 9, for negative 1, we also have this one. So it's okay because this is because the sparse for tensors also support the indexing, and also for the diagonal part, we just remove this dot, and it's okay. And then we have to consider lambda up, and this is okay because if you execute it, and you will find that lambda up is also a tensor, but then this is not allowed. You will see you have some errors. This is because this operation, this is actually an in-place operation, and in computational graph, it does not support in-place operations for most of the tensors. So we need something else. And in ADCME, you can do something like this. Scatter update. And you place the update you want to update lambda up at location 1. And what's the update? The update is just a lambda up 1. And actually this is equivalent, and actually I should add the quotation mark here, is equivalent to this syntax. But you cannot do that because this is an in-place operation, and yeah, essentially you don't know how to do the automatic differentiation of in-place operation because everything is changed. You do not have intermediate values. Okay, so let's say if it works. Okay, you can see that it works. Okay, so now we create A. This is something different. It's the sparse tensor, not the original one is actually a sparse CSC matrix, which is a numerical matrix in Junior. But here, this tensor is in ADCME instead of Junior. And the benefit of this tensor compared to the sparse arrays is that this tensor supports automatic differentiation. And so we can just backpropagate the gradients into the entries of this matrix. Another very different aspect is how to do the for loop. Actually, you can do the for loop like this, but just like specify, because we cannot do as we said, we cannot do in place operations. So we have to collect U as an array of m plus one tensors. But here we want to something efficient. For example, if you want to just write a for loop, and the computational graph will look like this. You have U1, U2, U3, until UM. That means you will create M computational graph, subgraph for this operation, and that can be very, very expensive, at least at the time of construction, because you have to iterate over all the computer, iterate over all the use and construct the computational graph. And a very good way to do that, a very efficient way to do that in ADCME is to use while loop, and that's actually a wrapper for tf.while loop, which is a way to write while loop by just constructing one computational graph and annotate it as a while loop. So let's see how we can do that. For while loop, just think of while. Actually, if you write this one as a while, it's actually while k is less than equal to m, and then you at each iteration you just increment k, and actually you need to global k here, maybe k equal 1. Yeah, and those two blocks, code blocks, are equivalent. So for while loop, there are two essential gradients. The first ingredient is the condition, the while condition. So you have a condition, and the input is always an index I, which is actually k, index k, and another is u. And u is a tensor array, which I will introduce below. Yeah, tensor array. So in the condition, you just write k minus less than m. Okay, and another is the body, and the while loop body. And for this tensor array, you need the value at the last time step. So what you can do here is to read from the tensor array, read uk, and this is what you have, and you get uk here. Another one is fk, and you can just write fk because we already have f here. Yeah, f here. Yeah, for convenient, we can just swap m and n, so that's the index. If you write fk, it's just the kth row, because in TensorFlow the arrays are stored in row major. So this is just just some convention here. Okay, if we have fk and uk, so we can assemble the right hand side. It's just uk plus fk. And what about a? You just write a. This is your u. Yeah, this backslash, it's simple here. It's just a backslash, but actually it contains a lot of information about this operation, because when you do backpropagation, you need to backpropagate the gradients through this backslash. And to do that efficiently, you should never do the inverse of a, because that will create a lot of inefficient operations. Like you do the inverse first and then multiply that right hand side by the inverse. And in the backpropagation, you have to differentiate with respect to the inverse. That can be very expensive. Yeah, there are ways to do that. Yeah, if you're interested, that's actually something related to the adjoint state methods, and that's a very efficient way to calculate the gradients with respect to entries in A. So let's say we already have u nu. So we have to store this u nu into this tensor array, because it's a storage. You can view it as a storage array. So you just write u at location k plus 1 u nu. So you have a u equal right, and remember, you have to return the body. When you return, it should return all the arrays, all the index in the same order as the input. So k should be incremented to k plus 1, and u is the new u after you write something into this u. So this is the condition and the body. So we have just created two functions, but we have to invoke while loop to do that. So let's say, what's the k here? The initial k should be 1. And we unit specify that as int 32. And also we need a tensor array, and you can create that with tensor array. And how many tensors will you store? It's actually m plus 1. Also, you need to give it the initial condition. So that's just you write the initial conditions. They are all zeros, and they are of length n. Okay. So the last step is to throw it into while loop. You have a condition, and you have a body, and you also have k and have u here. And the output is the same as k and u. So because k is never needed, you do not need a k. You already know that is m. It's m plus 1. So you just put it here. And for u, it's just a letter u. Maybe I just call it u out. Okay. So u out is actually a tensor array. To convert it to a value that you want, because in Hit equation we just have an array value of u. So we just want to make it an array. So we just call stack u equal u stack. But we'll give it a new name. This is just a u array, and the u array will be a tensor array instead of a tensor array. So maybe at this point, let's you execute it and see what happens. It's Hit equation. ADCME. Okay, something wrong here. Let's say, yeah, we should uncomment it. Okay, you see that u array is just the array with shape. The first dimension of the shape is unknown. The second dimension is 50, which is exactly what n is, what this n is. Yes. So, but we know that the first dimension is m plus 1. It is unknown here because TensorFlow does not know when your iteration will end. For example, it may end depending on the value of u. So it may end earlier than m plus 1. So it just the first dimension is unknown. Okay, so but we know that, so we can just set shape, just give it a shape so that it becomes something we know. The first dimension will be n plus 1, and second dimension will be n. So if you execute that, yeah, you have this one. So what's the left hand side? Left side. The left side, where we place the thermometer, is just a U array, because the first dimension is time and the second dimension is the location, so it's the first location. Okay, so this is what we want, left side. So let's see what we have. Left, yeah, to know the values, we just create a section. And after you create a section, you want to populate those values like 5 and 2 into A and B. So you init sys, okay, and you run sys left side, and this is because here at this point it's still tensor, but after I create a session and I run it, it becomes a value. Okay, let's see what we have here. Plot left side, and we save it. We should first close everything. This is, yeah, let's say this is temperature, so we have temperature from ADCME. Okay, so let's run it. Let's see if it is the same. This is from our ADCME program, and this is from from last program. Maybe I'll rerun it. Rerun the first one. Yeah, rerun it. Let's see if they're the same. Yeah. Maybe I just make it larger. Okay, you can see they're exactly the same. 0.8.